Our guest today is Gustavo Dalpian, a friend of ICTP-SAIFR and IFT. So as usual, I'm going to introduce a little bit his career. So he got his master and PhD in USP. And his thesis was about the properties of semiconductors. And for that thesis, he also got a prize from the SBF, right, for the best thesis of 2004. Then he had a couple of postdoctoral appointments, all of them in the US. The first one in the National Renewable Energy Laboratory, and the second at the University of Texas in Austin. And then he came back to Brazil, where he's now a full professor in USP. He's an expert in material science and condensed matter, and I came to know him because now he's interested in application of artificial intelligence to condensed matter, right? And the talk today seems to be in that direction. The title is Materials Informatics. Gustavo, the floor is yours.
Okay, thank you, Dario. So it's always good to come here to IFT and meet friends, and so I'm very happy. Thank you for inviting me to come here. Here it is. So the idea today is to talk a little bit about materials informatics. So I try to organize a very general colloquium just to show you some ways how to use these data science tools and machine learning in the area of material science. So the idea today is this. Let's see how, I'm going to show you a few different ways to use this kind of tools. Some are going to stay, some were just fancy toys, and but others, I think they are coming to stay, and it's worth showing you what's being done, okay? So let's go. Oops. Okay, let's see. Oh, no, this is mine actually. So I think it's out of battery probably. Okay, I can change here. So before starting, oh, let me start my timer here just to. So let me tell you a little bit about what we do. Okay, let's not mix them here. Yep, oh, thanks. So let me just show you very briefly what we are doing there at USP. So we work basically in the area of computational material science, and we are working mainly in three big directions in our group. So one is materials informatics. That is the topic of this talk today. So it's some way of merging material science, condensed matter physics with data science tools and machine learning. So this is one way we like to work. So there is another front that goes through the direction of quantum materials. Once some friends told me, what are quantum materials? So all materials are quantum, so what is the idea here? So, well, it's a fancy word. Maybe it's better to talk about strongly correlated systems and things similar to that. So quantum materials sit somewhere in between these different kind of fields. And we are also working a lot with focusing on materials for energy. We have a lot of works focusing on halide perovskites and so on. So this is the team that is working with us there at USP. And we currently have a thematic project here from FAPESP. Materials by Design is the name of the project. Alexandre Haley is part of this thematic project here. And we also have an INCT from CNPq, and Alexandre Haley is also part of this project here. So this is our main funding for our research. Well, the idea today is talk about materials. I work with materials, so I'm always very happy to discuss materials. And I like to start way back in history. And I like to say that many of the main advances in human history they were based on the ability of humankind to deal with materials. Even if you look for prehistory, different ages are divided depending on the type of materials people were able to work with. So you have the Stone Age, when people were able to start working with stones, and then you have the, I think it's brass. How do you translate to English? Huh? Iron Age. Iron Age, where people started working, dealing with iron and making tools for agriculture, war, and so on. So materials are very important. Nowadays, if we go to any device such as this one that we have, everyone has a cell phone, so it wouldn't be possible to have this kind of cell phones if it weren't for the development of many of different types of materials. So you have the batteries, lithium batteries. You have materials for the speakers. I mean, you have very strong magnets that made it possible to put very powerful speakers here in these cell phones. You have polymers for the case. You have transistors. Even this glass, the glass of these cell phones, it's called Gorilla Glass. So it was developed based on a lot of studies regarding material science, okay? So materials are everywhere and they're important. That's the idea I wanted to tell you with this brief introduction. So what is our vision of materials? How we would like to approach material science? So we would like to, and this is the way we were trained. I was trained 20-something years ago. We would like to study and try to understand materials from an electronic structure point of view. So what we have here, or the tools we use are basically based in quantum mechanics, and we would like to understand what each electron is doing inside a material. Together with these methodologies, the quantum mechanics, we observed a very fast development of computers. So every day we have more powerful computers, and putting these two things together, we can do a lot of new science and interesting science, okay? So when we talk about electronic structure, we have what I like to call a preferred method to work with this kind of systems. And this method is called density functional theory. So this is the basis of our basic quantum mechanics tool. And it was developed in 1964 by Walter Kohn and collaborators. And Walter Kohn won the Nobel Prize in Chemistry a few years, actually it's almost 30 years ago, for the development of this theory. And the idea is to solve this kind of equation where we use an auxiliary non-interacting system. So these are non-interacting wave functions. I is related to each electron. And all the many body interaction parts, they go to this term here. But I'm not going to talk a lot about this. Just to tell you, what I wanted to tell you is the following. This method, this density functional theory method, it's very good, okay? So we can predict the properties of materials in a very precise level. It works very well for studying materials, for studying atoms, for studying molecules. It's a very good tool. Even chemists, they like this method. So usually chemists, they like to work with a higher degree of precision, and they also like it. So if you look for theoretical works on material science, materials chemistry, condensed matter physics, it's very likely that people are using this kind of methodology. So, yes, Nathan. It's not put by hand. Actually, there are a lot of different flavors of VXC that you can put here. So this is, in density functional theory, this is the most active area of research nowadays, still trying to find good potential, exchange correlation potentials. So there are a lot of different, there are dozens of different methods and potentials. And when I say that they have predictive power, it's not for all properties, but many properties we get a very good degree of precision. For instance, if you want to compare phase stability among materials, if you want to get distance among atoms, so you get very good results here, okay? If you want to calculate band structures, effective masses, you get very good results from here. On the other hand, if you look for band gap, that is the energy difference between filled and empty states in a material, then this is not very good. But we know it's not very good. So the absolute value is not good, but when you compare different materials, like if one has a larger band gap than another, you calculate both are going to be smaller, but the order is still good. So it has predictive capability. This kind of methodology with limitations, okay? It's important to know that we still have limitations, but it's every time it's getting better, okay? So as we have this tool nowadays, and we have very good computers, so a few years ago people realized, you know, we can get a lot of data by running this kind of codes and studying materials in different configurations, trying to invent new materials. So people started realizing that the quantity of data they were producing was so large that they could not use the same methodologies they were using before to analyze this data, just too much data. And then it came a time when people thought, we need new tools to analyze this data. And that's where materials informatics started. That's where when you put together this area of electronic structure calculations, condensed matter theory, together with data science, okay? And the main milestone, I would say, for this area is this project. It's called the Materials Genome Initiative that was launched during the Obama government in the US in 2011, so it's already 15 years old, okay? And this was the starting point of the whole area of materials informatics, okay? So there is a slide that I always like to show you that shows that this is actually a new way of doing science. It's actually a new paradigm in science, okay? So this image was taken from this review. It's a very good review from a Brazilian group that discusses machine learning and this density functional theory that is our tool for studying this. So the idea is that what we are doing now is a new way of doing science, is a new paradigm of science, where you have the first paradigm is experimental science. This is the oldest one and most basic one. Then you have theoretical science, and where you try to write some equations to understand the science or the nature of the problems you want to study. So you have Maxwell equations and so on here. But at some point, it became too hard to solve these equations, and then people started using computers to solve these equations, and that's the third paradigm of science, that is computational science. Okay. But at some point, computers started generating too much data, and people couldn't use standard ways of analyzing the results here. And then where the fourth paradigm came, that is data-driven science or big data science or machine learning and so on. So that was a very long introduction just to show you that what I would like to discuss in this seminar is what can we do here with this fourth paradigm of science? How can we deal with this kind of science, okay? So the idea, when we talk about materials informatics, the most important, the first thing we think is artificial intelligence. Materials informatics is not only related to artificial intelligence, it can be much broader than this, okay? But when we started working with this a few years ago, my students came to me and said, come on, Gustavo, why do we have to use artificial intelligence to learn a property of a material? Just tell me the material that you want to study, and I'll go to the computer. A few minutes later, I come here and I tell you the results. I mean, it's not that it's that hard, right? In material science, the way we do machine learning with material science is different than in other areas because the quantity of data is much smaller than what people have in other areas. The other day, I was looking people analyzing images from galaxies and trying to predict the form of galaxies. And I mean, how many galaxies you have? You have, I don't even know, billions probably, or even more, right? So it's useful to try to use some automated tool, artificial intelligence, to study this. If you go to material science, the largest databases, they have 100,000 materials on it. So it's orders of magnitude difference. So it's not the same way. The way we do this is not the same way. The idea here of this cartoon is that a simple prediction of properties is not good enough for what we would like to do. Okay, if you take the cell phone and say, open your photos and say, find the cat in the photos. So artificial intelligence is important for that because you have a lot of photos. You don't want to spend time looking at all of them, and so it's important. But for materials, it's not like that. At least I think it's not exactly like that. So what I'm going to show you here is a few different ways we can work with in this area of materials informatics, a few different ways we can use these tools to study materials, okay? So one of them, the first one is data generation. I mean, there is still a lot of space for generating data. If you want to do material science, you need data, and that's there are still opportunities. Another one is prediction and acceleration. That is important, although I don't think it's that cool. Natural language processing, that is ChatGPT, this kind of things. This is very hot topic. And this is one of the one that I like most, interpretable machine learning. The idea is to try to learn new physics from machine learning, not only predict in which picture there is a cat, but try to learn how computer thinks, to learn how to identify the cat. And we can do that for science as well, try to learn new physics based, trying to understand how computers do their business in machine learning. And just at the end, this is the hottest topic. I'm not going to talk a lot about this, but I think this is the one that is going to last more time and is going to be more important. And there are more people working with this, that is machine learning potentials. Okay, data generation. There are a few repositories all over the world of materials. The most important, I like to talk about this one, is ICSD, Inorganic Crystal Structure Database. So suppose you have an experimental group that discovers a new material, okay? They grow a new material. The first thing they do is put on an X-ray machine and try to get a diffraction pattern to understand what is the crystal structure of this material. So how are the atoms distributed over this lattice? So this is the most basic thing people do. And so they make this kind of analysis, and they put this experimental data in this ICSD database. And so this, it has around 100,000 materials in it, okay? Then what people did is they build a robot that took every entry from this database and run some ab initio calculation to get the physical properties using density functional theory, for instance. And then you have these other databases like, let me see, materials design, no, materials project, I don't know where it is. Ah, here it is, materials project, that these databases, they have all the calculations, all the materials, all the calculations for all the grown materials are here. And the cool part of this is that computers accept everything. In the lab, atoms don't stick together sometimes. You cannot grow any material you want, but computers accept everything. So you can simulate a material even if it doesn't exist. Then you learn that it doesn't exist, basically. So what we did a few years ago, this was probably the first database, a Brazilian database of materials. So it's not a database. My students, they say it's a catalog because it's not that big. But the point is the following. It's very hard for us to compete with these big projects from these big databases. I mean, all the materials have been calculated here, so there is no point in repeating all these things again. But there is still space for calculating very specialized properties of materials. So that thing a robot did, and it was very basic. Here, we go one step beyond, and we try to calculate some more complex properties of materials, and then we report this more complex of these materials in a smaller database, a focus database, and we publish this in this journal called Scientific Data. And it's a very interesting, it's a different journal, because the editor said, you know, your paper doesn't even need to have science in it, it's just data. But here we made some Bayesian analysis, and so it's more interesting. But the problem with databases is the following. It demands a lot of work for you to build these databases, because it's not only, I mean, you could run the calculations and take all the data and send a zip file to someone, here's the database. That's not how things works. You have to work on it in such a way that people can use this data and analyze this data. So it's a big effort. I think this is the paper in my career that we had to invest the larger amount of man hours, everyone working here to get to these results. It's huge amount of work, huge amount. Nathan? With what? Yes. Yes, yeah, let me show you here. So let me go through. So just to understand this database, the idea is the following. So we wanted to calculate a specialized property of materials. And we wanted to calculate the spin splitting, intrinsic spin splitting of these compounds, okay? So the idea of calculating the spin splitting of compounds is for applications in spintronics and things like that, okay? I'll not enter a lot of in details. This, I like to say it's enough for me, it should be enough for me to say I want to calculate a very basic fundamental property of material and put there, and if there are applications, it's better, but it's good enough this way, okay? And then the idea is the following. If you take a material, a semiconductor, this is a representation of the band structure of semiconductor. And this is in reciprocal space. So here you have, it's two-dimensional material. So you have just two K vectors, Kx and Ky. And these represent the band structure for spin up and spin down. So most materials, they spin up and spin down, they are degenerated. Okay, they have the same energy. Both bands are degenerated. But sometimes you can break the symmetry. I mean, Zeeman effect we studied in quantum mechanics. You apply a magnetic field, or there is Rashba effect. You apply an electric field, and then you break symmetry again. Okay, so there is a spin splitting here, and we wanted to calculate the spin splitting of all these materials. This is not new stuff. I mean, So what we do is the following. I'm going to skip this. So we start, there is a database where there are all the chemical formulas there. There is a database called C2DB where they report all this, they report the crystal structure for all the two-dimensional materials. So, but it's just the basic structure. In order for calculate the spin splitting, you have to do more specialized analysis, not straightforward to get this. And then in this database, they don't get this kind of more advanced properties. It's just the basic properties. So we start from here, and then we look for what is necessary to have for a material to have some spin splitting. And then we run all these calculations. It's a little bit. So here in the database, there were almost 4,000 entries, 4,000 materials, only two-dimensional materials, and we get something like 400 or something like that. And then we classify all these materials depending on the type of spin splitting. There are some algorithms to analyze. We have to analyze the symmetry of the material, symmetry in reciprocal space, and everything. And at the end, we get these huge tables. Actually, there are tables. There are JSON files that are specific for databases. So we generated everything, and it's been made available online. So I think there is still space for calculating highly specialized properties of materials, okay? Just the basic properties of the materials, they are all here. They are all here. But if you go one step beyond and make some more complex analysis of what you have, there is still place for this to be done. Yeah, well, here we have how many. No, it's not, definitely not all of them. Definitely not all of them. I would say that for you to check this, you have to use an experimental method called ARPES. That is a very specialized method. Here in Brazil, only in Sirius, actually not even in Sirius, I think they can do it yet. It's not working very well yet, but it's very hard, and only for field states, not for empty states. So I would say that 1% maybe you can check that. Yeah, but one thing that is interesting is the following. What we did is the following. Once you have all this data. I don't have all the slides here to show this, but the idea is that we started analyzing the results and try to infer what crystal structure would lead to a larger spin splitting and what kind of atoms would lead to a larger spin splitting. So that's where Bayesian optimization enters, and we try to propose new materials that would have a larger spin splitting than the ones that are already known. So the idea is to propose new materials for experimental. This has iridium. It's not very good. Iridium is not very, it's hard to get, okay? I think iridium only came to Earth through meteorites. There is yeah, some story like that. So iridium is very hard to get. But we can go beyond. So we can, the idea here is trying to propose new, once you get the information from all materials, you can propose new materials to get, that would have the property that is our target here. Okay, another way of working with this prediction and acceleration, I mean, as I told you, you can easily calculate the properties of material, but we can use the databases that we have to train machine learning models and predict if a material will have one or other property. Here, what we did is we trained a model to predict the magnetic ordering in two-dimensional materials, okay? We wanted to predict first, this magnetic two-dimensional materials. There has been a lot of discussion in the old times. Who teaches statistic mechanics here? He's not here. Alexandre, okay. So there is a discussion that there should not exist magnetic order in two-dimensional materials. That's Mermin and Wagner theorem, something like that. Although, and then recently, it has been shown experimentally. So this is 2017, 18, 16. This is a little bit, but it's still recent. They observed magnetic order in two-dimensional materials. Obviously, anisotropy here plays a role, and then you can. It's not a dilemma anymore. Okay, but this is very fancy. This is very hot topic. A lot of people studying magnetism in two-dimensional materials. And what we wanted to do is the following. We wanted to train some machine learning model to predict whether a material is going to be magnetic or not. Okay, very simple toy here just to train the students. It's as I'm going to tell you at the end, I don't think this is very useful nowadays, okay? People are not using this. I mean, there are a lot of models trained to predict some properties, but people don't use it at the end. So it's not exactly a word, but that's a way of, there are a lot of works similar to this one, okay? So you first predict whether a material is magnetic or not, and then we wanted to predict whether it would be anti-ferromagnetic or ferromagnetic. And at the end, it worked, okay? So we can do that. We use this, the same database of materials. We have to tell, the idea is we just tell the computer, we train our model just with the type of atoms, the chemical formula of the material, and the crystal structure. So we use only this information to train the model, and then at the end we can get whether the material is ferromagnetic or not, and so on. And we try to learn a little bit, so that's a little bit disappointing at the end. We try to learn, okay, what is important for a material to be classified as magnetic? And then we do this SHAP analysis, that is explainability, a way to explain the results. And these graphs are very complex to be analyzed, but here the idea is the following. For a material to be, if a material has iron on it, it's very likely it's going to be magnetic. But this is obvious, okay? So it doesn't help. This, everyone knows this, so it just doesn't help a lot, okay? So we can go and try to learn what are the structures that lead to magnetic structures. We can make some analysis like that. And for predicting ferromagnetic versus anti-ferromagnetic configurations, this is much harder, okay? And we had to take our database, divide it in smaller portions, and then use these small portions to train our algorithm. But this is very hard. This is much harder to do. And we even had to change methodology. But the idea is the following. Proof of concept, you can train a model, a machine learning model, to predict whether a physical property of a material, period. Okay? I don't think this is something that's going to last a lot of time. Now we give this kind of projects mostly to our undergraduate students just to train, okay? So, but it's just show, the idea here is just to show one way of working with this machine learning nowadays. Then we came to this natural language processing. This is a very hot topic. And what we did is the following. We used natural language processing to try to learn about CO2 reduction from the scientific literature. This was the work of master students. Lucas, now he's in Finland doing his PhD, okay? And the idea is the following. When, well, CO2, we want to get rid of CO2 because of greenhouse effect. And one of the ideas for getting rid of CO2 is to use a metallic surface, and then you throw CO2 on top of it, and there is a reaction on top of the surface, and CO2 can be transformed in other types of molecules. This is a very, very hot topic in material science and chemistry as well, okay? And so I told the students like that, okay, Lucas, let's study. It was a project funded by the Brazilian oil agencies, ANP. And then I told him, okay, we have to study CO2 reduction. I'm not an expert in this area. And then I told him, he asked me, what paper should I read first to try to study about this? And then, I don't know, let's go to the literature and try to find an important paper about this, and let's see if we can learn something. The other day he came and said, okay, Gustavo, I found 14,726 papers. Which one should I read first? And then I said, well, I don't know. I don't know exactly which one you should. And then we came with this idea of using artificial intelligence to try to extract knowledge from all this literature. And we realized this is a very hot topic actually in computer science. So a lot of people have been doing this and trying to build models to get and learn from the literature. The fancy term is the following for FAPESP, to try to extract latent knowledge from the literature. So the knowledge is there, but you don't know, people don't realize knowledge is there, okay? And then the problem actually with this work was the following. It's interesting that the hardest problem was getting the 14,000 papers. I mean, if you have 20 papers, you go online and click in each one, you get the PDF and you download it. But if you have 14,000, you cannot go there and download all the papers. If you had an army of students, you can, okay, each one get 100 papers, and then, but that's not how it works. And then you can build robots. But then when you build robots to download the papers, the editors, they block you. They realize it's a robot, and then they don't allow you to download all the papers automatically. And then one day, Lucas came to me and said, Gustavo, I got this 14,000 papers. Oh, that's great. How do you did it? No, I went to Sci-Hub and downloaded all of them. No, then Sci-Hub accepts the robots. And then I told him, okay, but we cannot publish a paper saying that we downloaded the literature from Sci-Hub, right? And then, oh, that's okay. So now it's okay. It's okay to be on YouTube. And then I had to call the editors, actually, right? So we contacted Elsevier, and we contacted Brito Cruz, that is now in, which editor? Springer or Elsevier, right? We contacted him, and we had to contact ACS, and then there were like 12,000 of these papers were in 5 main editors, and then we got from ACS, Elsevier, and Springer, I think, that were the most important ones. And then we downloaded all the papers, and we started working with the data we had. And actually, this was a very exciting work, you know, because we started using a methodology from computer science that was regexes, regular expressions. The idea is that you train you tell the code where to look for the information that you want. And then at some point during his master thesis came ChatGPT and everything changed. So nowadays that methodology is not used anymore. I mean, ChatGPT and these large language models came and these kind of things all get substituted. So actually this is an interesting thing that we could, at USP we are discussing this. Because when you use ChatGPT to analyze the data, or any Gemini or any other, so there is this way we do. I mean, I imagine many of you, if not most of all of you, are using this kind of technology nowadays. But when we want to do it professionally, let's say, for analyzing a large amount of data, you don't use the keyboard as we use. You buy tokens, and then you train algorithms to interact with the model, and it's very expensive. So people have been discussing that universities should buy a subscription of these large language models, you know, for us to be able to use the models to do science. And at USP, the guys from astronomy are discussing this very actively to see whether this would be possible. The idea here is like just to show you we can do a lot of analysis. So if you take we want to search, like this is the substrate, just to remember. There is a substrate, okay, and there the product. So there are some atoms in the so we can retrieve automatically for each substrate what is the percentage of each product that is produced. We don't want to produce hydrogen, for instance. We would like to produce other things. And we can try to discover new materials and see whether there is some new things coming from this. So this is, I think this is a very hot topic. If you go to computer science nowadays, there is a lot of people going to this area of language processing, and this is probably something that is going to stay as well. Oh, let me rush on. So this is one part that I think is the coolest one, although it's probably the the hardest one to work with. It's called interpretable machine learning, and the idea is we would like to learn new physics from data, okay? And then we decided to analyze a very basic problem in condensed matter, okay? So every time you have a semiconductor, what is a semiconductor? Here is a semiconductor has a band gap, that is the energy difference between filled and empty states. And this band gap can be classified in two different ways. There are materials who have direct band gap, and are materials that have indirect band gap. So what does this mean? This is the picture, this is, and this one, they are the pictures of the band structure of a material. Here I forgot to put, but this axis is energy, okay? And this is the path in reciprocal space. These states here and here are field states. Then you have the region of the band gap. There is a region of energy where you don't have any states. And then again, you have the empty states, okay? And these look like spaghettis, and so this is the band structure of the material. Direct band gap, the highest occupied level, this is the highest occupied, and the lowest unoccupied, they sit at the same point in reciprocal space. Indirect band gap, each of these ones, they sit in different points, okay? So this is qualitatively different, and this is very important for applications. Materials that have indirect band gap, like silicon, they are not good for optoelectronic properties. You cannot make a LED from silicon. So this is a very fundamental property. It's in every textbook, but no one understands why some materials have direct band gap and others have indirect band gap, okay? Very, very basic property. And then we decided, let's try to learn this from data. So, okay, let's use statistics to try to learn this. And then we published this paper. And this paper was published from people from computer science. Most times we use ourselves the methods, the algorithms. Here it was different. Mario and Fernando, they are from computer science, and they developed this method called the VAX method. That is a way to analyze and try to interpret data from machine learning, okay? And basically what it does is it evaluate patterns in random forests and try to learn new physics from it. I'm not going through details from the methodology because I don't have a lot of time here to do this, but the idea is the following. We go to a database, we download all materials that have direct band gap, we download all materials that have indirect band gap, and we train an algorithm to predict if a material has a direct or indirect band gap, as we did before, okay? Exactly as we did before. To train the algorithm, what we do is the following. We tell the machine learning algorithm just what are the atoms. So suppose you have a material that has chemical formula AB, or it could be AB2. So this is sodium chloride, for instance. This is silicon oxide, okay, and so on. So atom A, atom B. And then we tell the number of electrons, and we use these features to train our algorithm. And you get a good result. But our database had around 10,000 entries, and with 10,000 entries, we could not learn a lot. So the idea is that the physics responsible for having a direct or indirect band gap in all materials, it might be different. It's not a unique thing. Then we divided our database in materials by symmetry. We only compared materials with similar symmetries. And then we get graphs such as this one, okay? So this comes from the method that we use. What it does, so very briefly, what it does here is the following. These are the features, for instance, the total number of valence electrons of atom A, the total number of electrons, the position of d orbitals of atom A, electron affinity, several different properties. Here, the yellow, the orange one is for direct band gap, and the blue one is for indirect band gap. And then by analyzing these images, what we do is the following. We can see that here, this feature, for indirect band gap, it has small values, and for direct band gap, it has large values. And then the guys from computer science, then they sent us this information, and this is the number of valence electrons, okay, from atom A. What does it mean? If the number of valence electrons in an atom is large, then it's direct. This is related to the following. If a chemical element has d electrons, okay, then the number of valence electrons tend to be larger because you have 10 d electrons. So if you have d electrons, the material will have direct band gap, okay? So basically, what happens is that when you look at the band structure, depending on the symmetry, the crystal field splitting of these d orbitals, these d orbitals can interact with the conduction band of the material and then making the band gap direct. So the conclusion here was that if a material has d electrons, there is a large tendency for it to be direct. And you know, it took us 4 years to get through this. So I don't think, so what people from computer science says is the following. So I asked him, can we get the response to our question just using the data that we are providing? And his answer was the following. Yes, you can always get, but you need to provide the descriptor, the physical property in advance. So for predicting if a material is going to be a high TC semiconductor, we could try to make an analysis of high TC superconductor. But then you should provide the information that is responsible in advance. It's not that it's going to discover a new thing. You just give all the properties, and it's going to select among all the properties which one is the responsible for getting superconducting properties, okay? Well, I think it's almost my time here, so I'm going to advance here just to very briefly another way. Okay, so just to end here, I think this is very powerful. It doesn't, there is a PRL from 2019 that already used this kind of things. So people entered data from the position of the planets in the solar system using Earth as reference. And then they throw these in machine learning, and the algorithm automatically changed to a system where the sun was in the center. So what they said is that they discover heliocentrism, so on and so on. So I think this is very hot, and we should put some effort on this. The last one, machine learning potentials. I think Alexandre knows more about this than me. So the idea is try to use ab initio calculations, and ChatGPT did this slide for me, okay? So I used machine learning to create this slide. And the idea is the following. Sometimes we want to do very expensive calculations, do ab initio calculations that depend on temperature and run for long times. This is very time consuming. And so the idea is that we would like to get some simpler model of this. And we use quantum data. Basically, we use the position, the total energy of the systems when we train the model, and we build these machine learning potentials to run larger systems and for longer times, okay? We are doing some work with Alexandre about the precession dynamics in halide perovskites. We should submit this paper soon. So I think this is definitely, from all the topics I've shown you today, this is the one that is going to last longer here, and it's already being used by a lot of different groups, okay? So I think that with that, I come to an end, and my objective was not showing any just a specific result here of a specific paper or thing that we published, but just try to give an overview. There are many different ways of using this kind of tools. They are important tools. We think we should teach these tools to our students, okay? But we should take care, because it's not, sometimes it's not needed. You can do science without it. It's a tool you have to use for where it's useful, okay, and not everywhere. But there are a lot of opportunities, and it's a good way of training our students. Okay, that's it. Thank you, guys.
Thank you very much. Some more questions?
So the DFT method you use is like 50 years old? 60s, 70s.
The basic theory is 64. It's Yes.
Okay, so, but there's a theoretical error bar with that method. It's not supposed to be exact, it's an approximation.
It's an approximation.
So can the machine tell you how to better that approximation? Can
Yes,
it give corrections to the...
That's a very good point, Nathan. Yes. So people are trying to use machine learning to, I have to go back here, to train, I mean, in quantum chemistry, people have very precise ways of calculating this term here, okay? In quantum chemistry is hard. Are you okay if I say quantum chemistry? But, okay. In quantum chemistry, people work, they have very precise ways of calculating this. So the idea is using machine learning based only on the density of the system to try to predict a good value for this exchange correlation potential. So there are people using this nowadays.
Okay, but even that formula, I mean, that formula is an approximation. It's some mean field kind of thing.
Well, the mean field...
I mean, it doesn't...
oh,
just,
okay, yeah, well...
So you could have two-body, three-body interactions that just ignores, right? Sorry? Yeah, they're encoded indirectly in V, but they're not exact. There's an error. So I thought the machine might be able to tell you how to change that formula to something more accurate.
But you know, density functional theory by itself is exact. Yes. Just this term is not exact.
So that means the formula is not exact. No, there's no, I mean, it's not fundamental physics. This is some approximation.
No, it's fundamental.
What do you mean?
No, that's exact.
You have individual electrons that all interact in a complicated way, and R is just some some field coming from all of them.
No, actually, can I? Yeah, so the idea is the following. So you formulate, so density functional theory is not this. Density functional theory is a concept that you can actually write essentially the ground state properties of any many-body system, provided you have, you're using Schrödinger equation. But provided Schrödinger equation is your fundamental description of quantum mechanics, then you're saying that you don't need to solve the wave function. An alternative way to solve the problem is by finding a functional of the density. So that's fundamental. Now, what Consham did was they said, okay, this is very hard to find because I don't know what the functional is. But what I can do is I can find an auxiliary system that has a perfect mapping between the many-body system and a non-interacting system with the same density. So that is also correct, provided you would know exactly what this VXC is.
Okay, so you don't need a wave function that depends on n parameters?
No, you don't. This is the fundamental concept of density functional theory.
There's a proof?
Yes. So there are two theorems that prove that. So that there is a perfect mapping between the density and the wave function.
Yeah, I skipped this part, so I went directly here. But that's the idea. Density functional theory is exact as the Schrödinger equation. But in order for you to solve it, you need some kind of approximation. In order for it to be useful, you need some kind of
So maybe we can rephrase Nathan's question by saying, can you use the machine learning? Yeah, I mean, you can use the machine learning to predict, to make better clues about the V that is better, right?
That's the idea. You can use machine learning to get better approximations for this exchange correlation potential. So
and once you get this better approximation, can you understand how the machine came out with that better approximation? That will be an extra step, right? Because we'll give you not only a clue on how to solve the problem, but also how to infer that is a better solution.
Yeah, I think I don't. With the methods that I know so far, I don't think that would be possible because basically what you give is a density or a charge density and try to predict from this charge density the exchange correlation potential. Nowadays, they use some formulas. So you give the density and you use some formula to get exchange correlation potential. And you could do that with machine learning, trying to fit better this kind of properties. There are other tools that people try to predict the density itself, okay? But then it gets similar limitations as other models. But for this, there is a lot of discussion, but I don't think, from what I know, it's still not possible to understand why it's better.
Why? Yeah, that would be really the next step, right?
So.
Because yeah, you could learn, let's say, new mechanisms or new yeah. Other questions, comments? Yeah.
Thank you, Gustavo, for coming. I would like to say to know about predicting materials properties depending on the way of producing them, using this method or machine learning. Have you studied?
What you mean is synthesizability, what people say.
Because properties also depends on the way the method of producing it.
Yes, well, there are some works in the literature that try to use natural language processing, as we have shown before, that they downloaded all the literature from material science, let's say, and then they build up a model to predict to analyze the way the material was synthesized for each of these materials. And then the idea is to try to predict if a material would be synthesizable or not. Okay, so this is one thing that has been done, and it's useful. This one is useful. Okay, so what you say is the other. Maybe it's a little bit different. So depending on the synthesis steps of a material, the properties are going to be different. That's. Yeah, well, if you grow let's say, silicon, and it should be always silicon, right? But then if you grow with a material and it's conducts through holes, and you grow to another materials, it conducts through electrons, then the way it's built is different. Ab initio calculations can be used to predict that. But machine learning, in principle, yes, it could be possible, right? But it's a lot of work, too many variables, too many variables.
Some more questions?
Well, actually, just a curiosity. So what is the conclusion about the direct or indirect band gap?
So our conclusion is the following. First, symmetry is very important, okay? So the first important factor is symmetry, okay? And then the second important factor is the existence or not of d electrons. So there is a strong, all the families of materials that we studied, always the existence or not of d electrons was important to explain why the material was direct. If it has d electrons, it had a direct band gap. And this is related, as I said. So you have the band structure of material, you have the valence band, conduction band, and then you have the d levels here, okay, filled. And then these d levels somehow, if you take, here is energy, here you have k space, and I don't know, L point is k space. So by symmetry, this level can interact with this level, okay? And then it will push these orbitals up and make the band gap direct. So it's a coupling between the d orbitals, filled d orbitals with the conduction band that seems to be the responsible for making the band gap direct.
Thanks.
Some more? Okay, if not, we can thank Gustavo again.
Thank you. Thank you.